is Jay Patel. This is my ML project demo for my project PulseFI. This is based on a research paper that I read a while ago. The research paper was about using Wi-Fi to remotely detect heartbeat of a person. I thought that was pretty cool, so I chose this as my ML project. I tried to add something new to it, which I will also show you as the slide goes. So to start off with, we have the system architecture. So the hardware is actually pretty simple. We have two ESP32 microcontrollers. The transmitter acts as a Wi-Fi access point, sending UDP packets 83 times a second, so like 83 hertz. The receiver captures these packets and extracts CSI. The CSI gives us detailed picture of wireless channel, including the periodicity of a heartbeat. So the way it works is that when a person breathes in and breathes out, there's a chest compression and decompression. So if a person sits in between two Wi-Fi modules and the Wi-Fi waves pass through him, there has to be some sort of periodic data that we can collect and use LSTM to train on it and then detect if we can predict the heartbeat. So before going any further, let me just show you how the hardware actually looks like. So here we have a breadboard. On this we have the ESP32 receiver module, and this is the pulse oximeter sensor module. So the pulse oximeter sensor module is connected to the ESP32 via serial in, and the whole thing is connected from USB cable to my laptop, which feeds the live inference data from our module directly to our machine learning model. In the paper, they didn't do a live inference of person. They collected the data set and then ran it later. So what I'm attempting here is that we can get some live output of how a person's heartbeat would be. This is the receiver module. Behind me I also have the transmitter module. This is placed at a distance of around 1 to 2 meters. Right now I've only trained the LSTM for a distance of above 1 meter, so that's what we're working with. Let's get back to the presentation. So this is the architecture that we have right now. Initially I did include the classifier in the project, but I had to take it out because it was not generating right data for me, and I had trouble running it perfectly. So right now I'm just using a regressor, which is an LSTM model that I have generated data set for and then trained upon. This signal processing pipeline is actually pretty interesting. Once we have the CSI data from our Wi-Fi module, we only use its amplitude because we can only detect that bit very precisely. We can also use phase, but due to clocking issues on both of the ESP modules, we cannot use that on this hardware. The whole point of the project is to make it as cheap as possible, so that's why we are using amplitude. We take the amplitude, we apply a Butterworth bandpass filter, then we apply one more filter to normalize the rate and to make it we get the corresponding frequencies to 48 to 130 BPM, and then we feed the data to a LSTM neural network to train it. This is the result so far. The classifier didn't yield good rate, but that's to be expected. The regressor, however, had a mean average error of about 14 BPM, which is far from perfect, but since we have a low amount of test data, which is only me, I think this was appropriate. In the original PulseFI paper, they had about 120 participants of 120 different subjects that whose data they used to train the network. We have a dashboard, and There are some techniques that I use to augment the data that I have right now. I also try to multi-thread it, and the main pipeline is to capture the data, validate the data, build a data set, add the data if necessary, merge everything, train, test, and then live inference. So this is the screenshot of how the the dashboard looks like, and we can just go to the demo right now. So this is the live demo of my dashboard. This data is being fed in real time from the Wi-Fi receiver, so you can see that the CSI packets are continuously increasing, that because it's continuously receiving information from the transmitter that I'm sitting in between. um, so the right now my predicted heart rate is around 94 to 95. We can so right now I'll go ahead and place my finger on the sensor and see what my actual heart rate is, and it should be around plus minus 14 of the predicted heartbeat. Of course, the sensor isn't very accurate either. So you can see there are dips in the sensor ranging from around 105 straight to 77, which is just not possible because my heart rate is pretty stable right now. Uh, but we have an average. I can average it out, so it is pretty close to the predicted when we look at the graph here. So when we look at the graph, we can see that um, it does match a bit there, and it is within the expected error range. Sometimes it gets very close to detection, sometimes it's even perfect. um, but that's just because we have a lack of data. So concluding this, so the future work that we have in that I have in mind is that we can test on different ranges of Wi-Fi transmitter and receiver. um, we can have more subjects that we can use as training data. So right now it's trained on just me, so it's overfitted to my heart rate right now. And the improvements that I can bring, another new feature that I wanted to bring was that the pulse oximeter can also measure the SpO2, so like the oxygen amount in your blood. We can collect that data and correspond it to the heart rate to get the oxygen of an individual wirelessly, remotely, non-intrusive method. So that has been my project so far. Thank you very much.